class, what we talked about was we discussed VSEPR formula and also molecular geometry, but I'd like to go back over that for a moment and talk about how we actually get those molecular geometries. And so what we're going to do is we'll move into and look at these different Lewis dot structures, because we need to start with the Lewis dot structure. And so as we start to make these Lewis dot structures, what we first of all figure out is that magnesium has 2 valence electrons, and so we put a dot on each side representing those 2 valence electrons. And with chlorine, what we have is we have 7, so 1, 2, 3, 4, 5, 6, and 1 for the bond, which gives us those 7. And same thing on this side, because we need another chlorine over here. And what's going to really happen when you bond a metal and a nonmetal together is that magnesium loses those 2 blue electrons and chlorine gains them. And so magnesium actually becomes a +2 charge. And so that's the Lewis dot structure for the first one. If we look at boron trifluoride, what I'm going to do is I'm going to just represent the bonds with a line. So there are 2 electrons in that bond, 1 electron from the boron and 1 from the fluorine. And so what we get is we get something that looks like this, including all the valence electrons of the fluorine. As we move on, there's methane. So methane bonds, there's a hydrogen. Okay. And we can keep going on as we get to NH3, which is one of the ones that we're going to talk about in just a moment about its consistency with the rest. And then finally, the last 2 that we have here are water, and water has 2 electron pairs that are not bonded, plus the 2 that are bonded to the oxygen, or to the hydrogens. And then the last but not least, we actually get a double bond between the carbon and the oxygen, and the same thing on this side with the carbon and the oxygen. Okay, what this leads to is now the opportunity to start talking about this valence shell electron pair repulsion. And what that means is that anytime you have a pair of electrons around an atom, they're going to try to get as far away from any other pairs that they can. And so if you look at the magnesium chloride, what we have is a pair of electrons on each side. They're actually going to repel each other as far apart as possible. And so here we have it, valence shell electron pair repulsion. And so that pair of electrons are going to repel that pair of electrons. And so what we get is we get a formula that is going to describe that shape that's actually going to be created. And that formula is based on the central atom, which we're going to call A. And so if we look at magnesium, magnesium becomes A, and each chlorine becomes an X. So magnesium chloride would be AX2. A being the magnesium, the X's being the chlorines. Now if we look at boron trifluoride, we have boron would be represented by the A, would have 3 X's tied to that. And if we go to the methane, methane has 1 carbon, it's got 4 hydrogens, so it's an AX4. So for the most part, this works pretty good because all we're doing is we're describing the central atom and how many atoms are bonded to it. So what we need to do next is we need to talk about, well, what happens when we have a pair of electrons coming off of an atom. And so as we look at this next one, we have a pair of electrons sitting up here. And so it's valence shell electron pair repulsion. So that pair is going to cause some repulsion of these other 3 pairs. And so we're going to describe it. So we're going to call that guy E. And so this is going to be an AX3. And then we have this pair of electrons. So we're going to call it AX3E. And again, if we look at water, here's a pair of electrons. Here's another pair of electrons. So there's 2 E's. So this guy is AX2E2. And then finally we have this carbon dioxide, which actually is simply an AX2. And so if we look at this, we're only describing the electrons on that central atom. Okay. Now, by knowing the VSEPR formula, it helps us to figure out the geometry also, and what this is going to look like in three-dimensional space. And so if we move on to the next slide, what we have here is a chart of all the three-dimensional geometries, or at least the three-dimensional geometries up to bonding to four things. And so what we're going to do is we're going to start out with a linear. Anytime you have two things bonded together, what we're going to do is, if there's only two things bonded together, what we do is we always call that linear. And so looking up here, we have an AX. So all AXs are going to be linear. There's only two things there. Hydrogen's an example of something like that. When we get to an AX2, there's actually three things bonded, but there's no pairs of electrons on that central atom. All the pairs of all the electrons around that A are actually are in bonds. So that also gives us a linear shape. When we move on to an AX3, what we have is three things bonded to this, and we have the A in the center, and what that gives us is what's called a trigonal planar. And that trigonal planar, the triangle, actually goes between the three X's. And then if you were able to spin that in three-dimensional space, it would stay flat. And it also, one of the other things to look for is the number of valence electrons around this would typically be 3. So this particular central atom would have 3 valence electrons. We move on to an AX2E2 or E, and what we have is what's called a bench shape. And what we're doing is we have a central atom, two things bonded, and this pair of electrons that's sitting up on top, and the shape gives us a bench shape. And it only considers the atoms bonding, not any other pairs of electrons. We'll skip over this next one and move to the AX4. The AX4, again, there are 4 things bonded to the central atom, no pairs of electrons coming off that central atom. And so what we get is we get this tetrahedral shape. And the tetrahedral, if I draw lines between the outside atoms, and I'll have to do a little dotted line back in here, you actually get this shape called a tetrahedron. And so AX4s are always going to give us tetrahedron. An AX3E, we have a pair of electrons sitting on top. We have 3 things on the bottom. This gives us a shape that we call trigonal pyramidal. There's a little triangle on the bottom, and then it stands up as a pyramid. And then the last one is an AX2E2. This has 1 electron in this bond, 1 electron in this bond from the A, and so for a total number of 6 electrons of the central atom. Again, this one is a bench shape. Okay? And so as we start moving through this and looking at these different shapes, what we're going to see is some characteristics that we're going to run into of their polarity, and that'll be the next thing that we look at. So I just wanted to show you this slide real quick, a little better visual than what we just saw on that earlier slide. But this particular slide shows the shapes that are going to be formed. Typically 2 valence electrons, or possibly 4. This one would be 3 or 4 valence electrons if there was a double bond. And then we have 4 valence electrons. And we'll stop this for now and come back to it when we start talking about polarity. So